Imagine training a model to find a tiny tumor in a medical scan. The tumor might be a fraction of a percent of the whole image, with everything else being ordinary healthy tissue. Now here's the trap that catches so many people. A model can score wonderfully on paper by simply predicting background everywhere and never finding the tumor at all. It looks accurate, and it's completely useless. Dice loss was built to stop exactly that failure. Today we're breaking down what dice loss is, why segmentation problems need it, how the formula works, and how it keeps models honest about the small stuff. The clearest way to understand dice loss is to compare it with the loss it so often replaces. The usual choice is pixel-wise cross-entropy, computed pixel by pixel. It averages the error across every single pixel in the image, which sounds perfectly reasonable at first. But when the target is a small region surrounded by a sea of background, a model can win that average just by labeling everything background, quietly ignoring the tiny object we actually care about. High accuracy, useless result. Dice loss takes a completely different view. Rather than averaging over pixels, it measures how much the predicted mask overlaps the true mask, focusing on the foreground region itself. That relative overlap stays sensitive to the small target no matter how much background surrounds it, so the model can't cheat by predicting emptiness. It has to actually find the object to score well. Let's walk through the idea itself, because it rests on one elegant little formula. First, you compare the predicted mask against the true mask. You're asking a simple question. Where the model says object and where the object actually is, how well do those two regions line up with each other across the image? Then you measure that agreement with the dice coefficient. It's twice the intersection of the two masks divided by the sum of their sizes, and it ranges from 0 for no overlap at all up to 1 for a perfect match. If you've seen the F1 score for classification, this is essentially the same idea applied to sets of pixels. Next, you turn that score into a loss. You simply take 1 minus the dice coefficient. A perfect overlap of 1 becomes a loss of 0, and poor overlap becomes a large loss, which flips a similarity score into something a model can minimize. And because minimizing 1 minus overlap is the same as maximizing overlap, the model is pushed to match the true shape directly, even for a tiny structure. It optimizes the exact thing we truly care about, the region getting drawn correctly, rather than chasing raw per pixel accuracy that can quietly lie to us. Now that we've seen the mechanism, 3 ideas capture why dice loss matters. First, it optimizes mask overlap directly through the dice coefficient. Instead of chasing individual pixels, it rewards getting the shape and region right, which is exactly what a segmentation model is ultimately supposed to produce. Second, it's robust to foreground-background imbalance. Because it looks at relative overlap of the target region, a small object carries the same weight as a large one. The endless background can't drown out a thin vessel or a small lesion anymore. Third, it became the standard for small structures, especially in medical imaging where finding a thin vessel or a small lesion really matters. It's frequently combined with cross-entropy for more stable training, giving you the shape sensitivity of dice together with the smooth, well-behaved gradients of the pixel-wise loss. All right, let's lock in the essentials worth remembering. Dice loss is a segmentation loss that directly maximizes the overlap between the predicted mask and the true mask. It's built on the dice coefficient, twice the intersection over the sum of sizes, and the loss is simply 1 minus that coefficient. Because it measures relative overlap, it stays robust to heavy foreground-background imbalance where plain cross-entropy would ignore the small target. It's often paired with cross-entropy and shines on small medical structures. If breakdowns like this help things click, Standarity.com is full of them.